Hello friends, welcome to fourth lecture of function. In this lecture of calculus, function part 4, we will be studying about combining function, shifting and scaling of functions before going to do the detailed analysis of quadratic function, trigonometric and inverse function, which we will be studying in the next lecture. So let's talk about how to combine function. Like numbers, function can be added, subtracted, multiplied and divided to produce new functions. And while dividing a function, we should take care of denominator, which should not be equal to 0. Suppose f and g are the functions, then for every x that belongs to the domain of both f and g, that is for x belongs to domain of f intersection domain of g, we define functions f plus g, f minus g and fg by the formulas given below. F plus g function we can write as f of x plus g of x. Similarly, for subtraction we can write f minus g function equal to f of x minus g of x, and for multiplication we can write fg of x equal to f of x multiplied by g of x. Notice that the plus sign on the left hand side of the first equation represent the operation of addition of functions, whereas the plus on the right hand side of the equation means addition of the real numbers f of x and g of x. Similarly, minus sign on the left hand side of the second equation represents the operation of subtraction of function, and right side represents the subtraction of real numbers. Now, in the case of division of function, we have to exclude those points from the common domain of both f and g where g is equal to 0. So, at any point of domain of f intersection domain of g at which g of x not equal to 0, we can define another function by the formula f by g of x equal to f of x by g of x, where g of x not equal to 0. Function can also be multiplied by constant c, which is a real number. Then the function cf is defined for all x in the domain of f by cf of x equal to c multiplied by f of x. Let us see one example for understanding the combination technique of function. Suppose consider two functions f of x equal to square root of x and g of x equal to square root of 1 minus x. We know the domain of f of x, which should be non-negative real numbers, that is from 0 to infinity, which is a semi-closed or semi-open interval, and domain of g of x is from minus infinity to 1, which is also again semi-closed or semi-open interval. Now, what are the points common to both the domain of f and g? So, by inspection we can tell the points common to domain of both f and g is closed interval from 0 to 1. So, look at the adjacent table where I have shown that how you will write the combination of functions. So, consider the addition operation on function, which we can write f plus g of x equal to root over x plus root over 1 minus x, and the domain is the common domain 0, 1. Similarly, for f minus g of x, we can write f of x minus g of x, that is equal to root over x minus root over 1 minus x, and here the domain will be the common domain, that is from 0 to 1 closed interval. And for multiplication, fg of x, we can write square root x multiplied by 1 minus x, and here also the domain will be closed interval from 0 to 1. And for division, we already know in case of division we have to take care of the value of x for which the denominator should be equal to 0. Here we can see f by g of x equal to, we can write square root of x by 1 minus x, and the domain will be from 0 to 1, but we have to exclude the point 1. That is why the domain will not be a closed interval, it will become a semi-closed interval. It will include the point 0, but it will not include the point 1. Now, how to draw the graph of addition of function? The graph of the addition of the function is obtained from the graphs of f and g by adding the corresponding y coordinates f of x and g of x at each point in the common domain. So let us understand the graph of the addition of function by simple animation. Here in the graph I have drawn f of x equal to square root of x, which is shown by blue color line, and g of x equal to square root of 1 minus x, which is shown by the red color line. Now I have shown here the graph of the addition of two functions, that is y equal to f plus g, shown by pink color line, and product by black color line, that is y equal to fg. Now how do we draw the graph of addition of two functions? So consider a point A in the x-axis which is in the common domain of the two functions f and g, which we already know from the previous slide, that is from closed interval 0 to 1. And we have already drawn a vertical line from A. Now first we will find f of A, which is the y coordinate of the function f of x equal to square root of x. Now what is f of A? F of A is the intersecting point of the blue color line and the line which is drawn vertically from the point A. Then similarly we will find the value g of A, which is the y coordinate of the second function square root of 1 minus x. Now what is g of A? G of A is the intersecting point of the red color line and the line which is drawn vertically from the point A. Now we have to just add these two values f of A and g of A to get f plus g of A. Similarly, to obtain the product of the graph of the function, we have to multiply the value f of A and g of A to get fg of A. Now another way of combining function is composition of function. If f and g are the functions, the composite function FOG, we can say f composed with g is defined by FOG of x equal to f of g of x. Now domain of composite function consists of the number x in the domain of g for which g of x lies in the domain of f. So think composite function as an machine which consists of two machines g and f, where the first machine will take the input x and produce the output g of x. And now the output of the first machine will be the input to the second machine f, and the output of the second machine will be f of g of x. Here always keep in mind that the input x you have to choose in such a way that the output g of x of the first machine should be in the domain, or you can say allowed input value of the second machine, which will produce the composite function. Let us see another diagram of composite function, which is the arrow diagram, where x is in the domain of g of x, and if g of x lies in the domain of f, then the function f and g can be composed to form f of g of x. Take an example, f of x equal to square root of x and g of x equal to x plus 1. So to find f composed with g of x, first find g of x and then find f of g of x. So look at the adjacent picture. What is g of x? As we have already written, g of x equal to x plus 1. So in the nearby picture we can see, if we feed x as an input to the machine g, it will give you an output x plus 1, and again if we feed x plus 1 to the machine f, it will produce the output square root of x plus 1. And here the domain of the composite function is semi-open or semi-closed interval from -1 to infinity. To see why the domain of f o g is from -1 to infinity, notice that g of x equal to x plus 1 and is defined for all real value of x. But g of x will only belongs to the domain of f when x plus 1 is greater than or equal to 0. That is to say, when x greater than or equal to -1. Let us talk about shifting a graph of a function. It is another a common way to obtain a new function from an existing one by adding a constant to each output of the existing function or to its input variable. The graph of the new function is the graph of the original function shifted vertically or horizontally as follows. So shifting formulas are, for vertical shift we will do y equal to f of x plus k, where f of x is the original function. So y equal to f of x plus k will shift the graph of f up k units if k greater than 0 and shift it down absolute value of k units if k less than 0. And for horizontal shifts, y equal to, we will write f of x plus h, which shifts the graph of f left by h units if h greater than 0 and shift it right absolute value of h units if h less than 0. So first we will understand how to perform vertical shifting. So let me show you an animation. Suppose if y equal to f of x and it is equal to x square. Now if we add plus 2 with the output of the function, that is the f of x plus 2, then the graph of the new function will be shifted up by 2 vertically. Now in the adjacent picture you can see the green color figure is shifted by 2 units up vertically from comparing to the orange color figure. And if we add minus 2 to the output of the original function, which is x square, the new function will become x square minus 2, and the graph of the function will be shifted down vertically by 2 units. Actually, by adding plus 2 and minus 2 to the graph of the original function f of x equal to x square, what we are doing? We are adding plus 2 and minus 2 to each and every output value of the original function f of x equal to x square. Now here I have drawn another graph by yellow color line. So now it's up to you to think what will be the function of this graph. Now let us understand how to perform the horizontal shifts of a function. As I have already told in the previous slide, that shifting a graph of the function can be performed by adding a constant value either to the output values of the function or to the input variable of the function. In case of vertical shifts, we have to add constant which can be either positive or negative to the output value of the function. And in case of horizontal shift, we have to add the constant either positive or negative to the input variable of the function. Now consider a same function y equal to x square, and if we add plus 3 with the input variable, that is x of the function, then the new function will become x plus 3 whole square, and it will be shifted left by 3 units. And similarly, if you add minus 3 with the input variable x of the original function, then the new function will become x minus 3 whole square, and the function will be shifted right by 3 units. So horizontal shifts can be easily remembered by remembering a simple formula. That is, add a negative constant to x will shift the graph towards right, and add a positive constant to x will shift the graph towards left. Now here in this figure you can see I have drawn again a graph which is shown by yellow color line. Now it's your duty to find what is the function of this yellow color line. Now let us talk about a scaling of a graph of a function. That is, how to scale a graph. Scaling can be performed either vertically or horizontally. Let us see the formula for scaling. So for c, which is a real constant greater than 1, if we can write y equal to c into f of x, then it stretches the graph of f vertically by a factor of c. Y equal to f of x by c compresses the graph of f vertically by a factor of c. Y equal to f of cx compresses the graph of f horizontally by a factor of c, and y equal to f of x by c stretches the graph of f horizontally by a factor of c. First, we will see the vertical scaling of the graph by an animation. So consider a function which is the square root of the x. Now if we multiply c equal to 2 with the function square root of x, we get 2 into square root of x. So how this graph looks like? It will be vertically stretched by a factor of 2. And if we divide by c equal to 2, then our original function will become square root of x by 2 equal to 0.5 square root of x. So how this graph looks like? It will be vertically compressed by a factor of 2. So look at the picture that at x equal to 4, the original function has a value 2. Now when the function is vertically stretched by a factor of 2, then the value of the new function will become 4 at x equal to 4 instead of 2. Similarly, when the graph is compressed by a factor of 2, then at x equal to 4, the value of the new function will become 1. So from this graph, we understand what is the vertical stretching of the graph and compression of the graph vertically. That is, at the same value of x, the output of the original function will be stretched by a factor of c and will be compressed by a factor of c. Let us understand horizontal scaling also. Let me show you an animation. Take a graph of square root of x function again. Now when we multiply c equal to 2 with the input variable to the function, then we will get a new function which will be equal to square root of 2x, and we can say the graph is horizontally compressed, which is shown by red color line. And if we divide input variable x by c equal to 2, then the new function becomes square root of x by 2 and equal to square root of 0.5x. Then we can say that the graph is stretched. So how can we understand that the graph is compressed or stretched now? Say at x equal to 4, the value of original function square root of x is 2. Now by compressing horizontally means that the same output value 2 for new function we will get at x equal to 2, because 2 is multiplied with x. So for every value of x as input to the original function, we get some output value. Now the output value same as that of the original function in case of compressed function we will get at x equal to x by 2. Similarly, for stretched function we can see the value of the function which is the original function, say y equal to square root of x, at x equal to 4, the output value of y equal to square root of x is 2, and in case of stretched function we will get the same output when x will be equal to 8. Now let us understand the reflection of a graph of a function. Reflection is a special type of scaling where the value of constant c is equal to -1. That means when we multiply -1 to the output of the function, say y equal to minus f of x, it reflects the graph of function f across the x-axis. And when we multiply -1 to the input variable of the function, that is y equal to f of minus x, it reflects the graph of function f across the y-axis. So let me show you an animation. Consider a function y equal to square root of x. Now when we multiply -1 with the output, then we will get a new function, that is minus square root of x, and the graph of the new function will be the reflection of the original graph along x-axis. And when we multiply -1 with the input variable x, then the function will become square root of minus x, and the graph of this function will be the reflection of the original function y equal to square root of x about y axis. Now when you multiply -1 to the original function, then the function will become minus square root of x. In this case, the value of the new function is the negative of the output of the original function. And when you multiply -1 with the input variable x, then your function becomes f of minus x equal to square root of minus x, and now your function will give you the output same as that of the original function when we feed negative value of x. So here in the graph we can see, suppose the value of the original function at x equal to 1 is 1. So the value of the function y equal to minus root over of x at x equal to 1 will be -1, and the output value 1 of the original function will be the output value of the function y equal to square root of minus x when x equal to -1. So thanks for watching, and please subscribe. In the next part of the lecture, we will be talking about quadratic function, trigonometric function and inverse function. So stay safe and stay at home.